Hi, I'm Debashish Dutta, and this is my final presentation for my network science project titled Network Analysis of City Street Layouts. In this project, I have employed the methods used by Alessio Cardio and others in their paper Structural Properties of Planar Graphs of Urban Street Patterns to analyze the statistical and network properties of um, street layout patterns of different cities. So, before I move on to the results, let me briefly discuss the methods that I have used. Now, for the different types of layouts, for example, San Francisco has a gridiron layout laid in grids, consists of like planned grids of perpendicular streets, whereas a place like Oldenburg in Germany, it has a medieval layout resulting from unplanned growth, um, which is usually the case in older cities. And lastly, San Joaquin um, in California, it has a lollipop layout. It's, it's a mix of grid layout and also consists of many cul-de-sacs and dead ends, which is a layout often found in suburban areas. I've used the methods discussed by Alessio Cardia and others in the paper um, to, you know, define properties of these networks like cost, and efficiency, and to quantify the differences. Okay, so for measuring the city street network properties, I followed the same. I followed the same approach as was followed by Alicia Cardi and others in their paper. There are three structural properties that I have analyzed in this project, and they are the meshness coefficient, the cost, the efficiency. In the paper, Cardia and others, they use the meshness coefficient in place of the clustering coefficient. This is the reason for this being like for many planar graphs, such as square grids and the tree, they all have a clustering coefficient of 0. Um, and we have used meshness coefficient here, which is defined as f over f max, where f is the number of faces of the graph and f max is the number of faces in the maximally connected graph. The cost is simply defined as the sum of the lengths of all the edges in the network. The efficiency, however, is defined by the efficiency of flow in the network, that is the ease of traversal from one node to another. The efficiency of a pair of nodes, say I and j in the network, is given by the ratio of the Euclidean distance of the two nodes to the shortest path um, of the pair of nodes in the network. The formula is given right here. Um, the figure on the right explains what I just said. The blue line here in this picture depicts the Euclidean distance between the two nodes in a network, and the red line it traces the shortest path between the 2 points through the network. The efficiency of these 2 points is the ratio between the two lengths. So, and the global network efficiency is the average of this ratio for all node pairs. So here are the results from my study. Here we can see the values for the various properties like meshness coefficient and the cost and the efficiency, where San Francisco apparently is like the most efficient of the three, and it lies in a sweet spot when it comes to cost and efficiency. let's see why. Um, so I've done like further analysis of the networks. Let's start with the betweenness centrality. So here you can see the distribution of the betweenness centrality of the three networks. And you can see San Francisco has a lot of nodes with high betweenness centrality, which means it those are the nodes that facilitate or will be there as part of the shortest paths for other nodes, thereby making it much easier for traversal. So the number of nodes is much more higher for San Francisco. This is a fun depiction of the node with the maximum between the centrality in the network. So this one's for San Francisco, this one's for San Joaquin. We can see like it connects these two clusters. So, and this one's for Oldenburg. Now, uh, coming to the node degree distribution, here we can see San Francisco and San Joaquin has a lot of nodes which are three and greater, which is typically true for any grid-like network. We'll have like four-way intersections, and not so true for old medieval networks like Oldenburg, which where most of the nodes will have a degree distribution of three because it's a three-way intersection. Now let's come to the cul-de-sacs and dead ends. This is another pictorial depiction of all the cul-de-sacs and dead ends for all the three networks. Here we can see it's the highest for San Joaquin. As I already mentioned at the beginning, it has a lollipop street network, a street layout, which means it consists of lots of um, dead ends and cul-de-sacs, which you can see here in the picture. Not so much for San Francisco and Oldenburg. Here's another analysis of one-way versus two-way streets. Here we can see like modern layouts like San Joaquin and San Francisco has a lot of one-way streets. So this might be one of the reasons for higher efficiency. When you compare it to Oldenburg, it doesn't have that many one-way streets. Here are some other statistics from the study. One thing to note here is the streets per node counts. So, like I mentioned earlier, this modern grid-like networks will have lots of nodes which are uh, four-way intersections, not as many in the old networks in Oldenburg. You can see here the numbers. It's much higher for San Joaquin and San Francisco. These are the credits. Thank you for listening.